this show on the road. Good morning, everybody. Happy Monday. I'm glad you guys are here. Hope you guys did okay with that last homework. Hopefully it made sense with components, right? Right, that the component notation tells you the pieces. So just to recap really quickly, right? If we have vector v, I can get rid of this. We're doing day 2. We're doing word problems and applications. So v, we said, right? So highlights from last time. In component version, right? We called it v1, v2, and the reason for that is it's the components. Now in physics, what we would do is instead of calling it 1, 2, we would say the x component of v and the y component of v, so it'd look like that, right? And you can think of these as delta x, delta y, right? So they're the components. So what we're saying here is that, let's say I had a vector with a point at the end and it was 2, 3, right? Then that would mean that was 2 over, that was 3 up, okay? So this is vector v. And that's what we were talking about last time. So vectors both have a magnitude and they have a direction, right? So for magnitude, so one thing I really wanted to point out here, some highlights from last class. Again, we're just reviewing last class. A magnitude vector v, remember, equals the square root of v1 parentheses squared plus v2 parentheses squared. Okay, and as you can see, this is just Pythagorean theorem, right? So in this example, it would be 2 squared plus 3 squared equals v squared. Okay, so it's just Pythagorean theorem. Cool. And then we talked about little properties like that were important, right? So this is not meant to be a lesson from what we did last time, but we did talk about some important properties, like with what we talked about scalar multiplication and addition and how to do all of that. So I just wanted to recap those big things. So what we're going to do today is we're going to take a look at, so there's component notation, and component notation is important. But there's also a more useful notation that isn't component notation. Okay, so that's where we're going to go. And are you guys doing okay? Do you guys have any questions before I get started? Okay, so what we're going to do today is here, just one second. So what we're going to do today is we're just going to take a look at a different form of what we did last time. So again, we're in the same section doing the same things, but instead of component, okay, we're going to think of things in terms of dimensions. And as we get into further and further math, we have to remember you guys have been doing math in 2 dimensions like almost your whole life, but we don't live in 2 dimensions. We live in 3 dimensions. So one thing to think about is if we have a 2 dimensions, right? So you're used to calling this the y and the x axis, but y and x, it turns out, have really important meanings, right? And the y, right, is can have different meanings, and the x can have different meanings. So rather than using y and x, what we use is I and j. Okay, so the I is your x-axis, and the j is the y-axis. Okay, so rather than doing v1, v2, what we're going to do is we're going to call anything with an I on it on the x-axis, and anything with a j in it the j-axis. Now, you might be like, well, why don't we use y and x? Because y and x are used for so many different things. We know y as being the output. We know x as being the input. Also, what happens when you start doing cross multiplication with x's? That gets icky. So j and I are the standard for doing coordinates. Now, you don't have to copy this down, and I'm going to do really terrible, so just give me a second. So if I had this going straight up, and then I have this going like this, and this going like this. So if this was I, and this was j, oops, lowercase j, and then this would be z. Oop, can you guys see that?
So this is your y-axis, this is your x-axis, and this is your
that's your z-axis, or your up. This is 3 dimensions, right? So this is 2-dimensional, because you imagine this being on a flat piece of paper, and then the 3rd dimension, z, coming out of it. Kind of cool, right? So we have I, J, and Z. Okay, now
we're not going to do 3 dimensions yet in this class because we don't have time to do that.
But what's important is now, instead of writing in terms of V1, V2, we can write in terms of I and J. So how would this look? So instead of saying V equals component form 1, 2, okay, what we can write instead is we can write, and I'm going to write it in a different color to be like an awakening, okay? We can write V equals 1I plus 2J. Oh, you know what I just realized? I think, oh, no, never mind. I said it was Z, but then that part of me wonders if it's K, but I'm pretty sure it's Z. Oh my gosh, but is it K? Oh no. Craft, don't lead them astray. It doesn't matter. It's either Z or K. It's either Z or K. You're going to be fine.
Doesn't matter. We're not doing that anyways.
Okay? So these are the same. You can see this one, though, is a little bit faster to write, and we don't have to do that. So from now on, we're going to use this. So this is called component form. Every book I've ever read calls this something different. I would just call this dimension form. I don't think that's an official name, but basically you're like going, okay, you're going 1 in the X direction and you're going 2 in the Y direction, okay? So, so again, let's just recap a couple of things with this. I just want to show you how to add really quickly with this. Okay, so these are the same thing.
So just to do a quick example,
let's say I have V equals 2I minus J, and let's say U equals negative 3I plus 8J. Okay, so we have 2 vectors. Okay, and notice their components are telling you what component they're in. And another reason why we switched to doing this too is that with this, it gets kind of awkward when you're like 1, 2, 3, because then you're like, okay, you have to remember the order. But here, you know, this is my X, this is my Y, and then if I had a Z or a K form, I would be in there. Okay, so I'm going to have you guys try this on your own and see what you can do. I want you to go V plus U, like that. We'll just do that. Oh, and do this one. Do U minus V. Okay. So I want you guys to find the answers. Just do that really quickly as like a little warm up, and then we'll do some harder stuff. Because really all we've done so far in this 8 minutes is just new notation. Can you do old stuff with the new notation? And then today we're going to focus on angles and word problems. Okay, so hopefully you guys are done or close to done. Sorry, I'm not being impatient. It's just what we're learning today is so much more important. So remember, when you add them, you combine like terms, right? And it's actually a little bit easier because like this is a lot more like algebra. If they look alike, you combine them. So here I'm going to have 2 plus negative 3. So I'm going to have negative I, and then negative j plus 8 is 7j, right? So it's almost easier. I mean, I think it's easier. That's why I'm teaching it to you. Okay?
And that's why the book uses it too.
So if I'm doing u minus v, remember with subtraction, that subtraction order matters. So we start here. So negative 3i minus 2. So that's negative 5i. And then 8 minus a negative 1 is 9i. Okay? Because we're getting rid of a negative, so we're getting more positive. All right. So with that, does anybody have any questions before we get into the new stuff? So again, just new notation, just practicing using that new notation. And then let's get into the new stuff, because you know what we haven't talked about yet was angles. So we have this new way that is a little bit more clear about what dimension we're in, right? We have component form. But now let's add our last component, and that is every vector has magnitude and direction. And that's what we haven't had, right? So to do direction, we would have had to draw it out and then use trig to find that angle, right? So what we're going to do is we're going to, instead of having to make pictures every time, we're just going to go straight to the chase and include trig into our vectors, okay? And that will complete our transformation of vectors, okay? So to do this, again, we use the unit circle because the unit circle is easy to understand, okay? Because if I did this without the unit circle, it'd be very abstract. So let's say I have a vector v, and it's always easiest to do in the first quadrant. And where it touches the circle is x, y. Okay, so that means that it's going to have some height, and that means it's going to have some width, right? Because this is two-dimensional. Now, this width is x, and this height is y. Now, that's what we've done so far. But if we want to include the angle, right? So right here, if I call this angle theta, right? How do we incorporate that into, right, that angle, that direction? Because if we're talking about math, right, our direction starts at the right, at 0 degrees. If we were talking about nautical, we would start at north, okay? But since we're in math, we're going to start from 0, and we don't have a lot of time. So here, how do we incorporate this angle into my v? Well, to do that, we use trig. So y is really sine of theta. Okay. And x is really cosine of theta. Okay, now, we don't have time to talk about this, but this is true if v is 1, right? Now, we're not going to have time to talk about this, but I know some of you have read the book, and you should be reading the book. So when it's 1, it's called a unit vector, and that should make sense because unit stands for 1. So this right here is considered a unit vector. Now, what you can do, and we're not going to have time with this, and we just don't have time to spend on it, but if this was a regular class, we would talk more about unit vectors. And the idea is, if you can get it down to a unit vector, you can multiply this unit vector by any number to get any vector. Does that make sense? So like, if this is my unit vector, I can multiply it by 5, and I get a vector that's 5 times longer in the same direction. Okay, so I hope that makes sense. So we always design things in the unit vector because we can just multiply to get whatever we want. And the reason why we want it in the unit vector is because then the math is really easy, right? Because then we can use a unit circle. And that's why. So if you were reading the book and you're like, man, these unit vectors don't make sense, they just do that so they can use the unit circle. Unit circle, unit vector. And then everything's really easy to do because all our trig is based off the unit circle. Again, so it's just for ease of mind. It makes all the math easy. So what does this mean? This means that vector v can be written as, cosine theta I plus sine theta j. Now you're like, why did they make them I's and J's? They look so much alike. You're right, they do. At least mine do. Okay? So, again, that's different than writing it as v equals x, y. Okay? So we're going to get more information. We're going to get the direction, because the direction is going to be the angle. And then we also have to remember that cosine of that direction is our the amount. Okay, so how cool is that, right? We can use trig, and when we use trig, we get direction and amount. And notice how I'm not saying magnitude, because magnitude is still going to be the square root, right? Okay.
Well, and so it's cool here if you're using the unit vector. The magnitude of a unit vector.
Because, right, what's a unit vector? A unit vector is 1.
So then that's just going to be the absolute value of v times cosine theta sine theta, right?
So remember, if we call this the unit, if we're in a unit circle and this is 1, you just take your magnitude and you multiply it by these coordinates. Okay, that's it. And that's the beauty of doing it this way. And that's the, I know I just said a lot, but I'm also not teaching unit vectors. So I just want you to know how this works, right? So if this is 1 and the math works really simple, then we just multiply those coordinates by whatever we want and we can get any vector. Okay? So enough of that.
Let's do some problems.
And what you're going to do. I hope that makes sense. Are you guys doing okay? That was a lot of talking. I'm so sorry. But I just felt like I couldn't teach this without talking about that. You know what I mean? Like, I felt like I was lying to you if I didn't talk about it. Are you guys okay? Does that make sense? Are we still... You guys always stop talking. Yeah, okay. All right. So that's what's going on here, is because if we do it, and this is the superior way, using trigonometry, and that's so that we can just multiply it by that and do that. Okay? So next up, so I'm going to give you guys 2 vectors. So let's say u equals 3i plus 3j, and v equals 3i minus 4j. Okay. So first thing we're going to do is find the angle for both vectors. Okay, so we're going to find the angle for both vectors. So what I'm going to do is I'll do one with you, and then you'll do one. Okay? So, so just really quickly. Oops, I always do capital. Okay, so I have I and j. So I'm going to go over 1, 2, 3, I, and go up 1, 2, 3, j. Okay. So this is at 3, 3. And then I get my vector. Okay, so this is vector u. You guys see how I did that? So it's 3 i's. I even said, like, it's difficult, and I warned you guys that I was going to make a mistake, so I really appreciate that you called me out on it. Okay, yeah, I did. I meant j. 3i, 3j. Thank you. So I have 3, 3 here, so I have this. So to find the angle, we're just going to do a little trig. So again, I want to use the right colors here. So I have 3 here, so this is 3, and then this is... Let's do it a different color. Let's do, this is 3. Okay. So then to find the angle, right, I want to use both of these. So I want to find angle theta. So that would be tangent of theta equals 3 over 3, right, which is 1. And then we have to figure out, when does tangent of that equal 1? Well, that's when theta equals pi over 4. And I'm just going to do one answer for now, because it's in the first quadrant, right? So if it's in the that's what I meant to say. It's in the first quadrant, so it has to be pi over 4. Okay.
So I want you guys to do this now for v.
So can you guys find the angle for v? So here, I'm going to put a timer, or else I'm going to rush you. So we're doing what I just did for you, and you're going to do it for V. And this is just practicing the basics. Make sure you guys know what you're doing. So that way, if questions come up, you guys can do that. And then we'll do our first word problem. All right, that should have been enough time. I want to make sure we get to these word problems. So again, we have 3 minus there. So when I take a look at this, I'm going to be going down, right? So I have I and J. All right, so I'm going uno, dos, tres to the right and down 4. So uno, dos, tres, cuatro. Not drawn to scale, obviously. Right, so I go here. And you can remember, I'm using a unit circle and then multiplying. So this coordinate right here is 3, -4. Right, so if I were to use fancy colors, the fancy color. And then I go, whoosh. So this is -4. This is 3. And I want to find this angle right here. Okay, so this is going to be a little trickier because remember we start at 0 degrees. So this angle is actually going to be this angle. Does that make sense? So we're going to find this angle here, and then once we find this angle, we're going to have to subtract it from 360 to get this angle here, right? Because remember, our directions are from 0, not from negative. Now we could just say it's a negative angle and we'd be good to go. So did you guys take that into account? If you make it negative, then your answer is correct. So this one would be tangent of theta would equal sine over cosine. Now, if I did this on a calculator, this would have been a lot easier in degrees, but I'd have to go tangent inverse of -4 over 3. Oops. Okay, so what do we get? -50. So you guys see how it's negative, it's down. So since it's already negative, I can just add 2 pi to that. And then I should put parentheses so it doesn't add 2 and then multiply by pi. Okay. Very interesting. What did I do wrong? I'm in degrees. All right. Hey guys, I'm in degrees. Okay. So if I'm in degrees, let's try that again. So if I'm in degrees and I get that, then I would add 360. Okay. So we get theta equals -53.13. So that's this angle right here. But then phi, the outside angle, that would be 306.87 degrees. I gotta put degrees there. Okay. So that's what's going on there. So again, the angle inside my triangle is this, but this right here, so this is the inside the triangle. This is my direction. Ooh, I can color with red and blue and get a 3D effect. Okay, that's our direction. Because remember, our directions are from the right. So to get here, right, to get this one, you would have to go all the way around like this and then get there. Okay, so remember your direction. And that's why we did this problem, right? If it's in the first quadrant, it's really easy. This angle is the same as your direction because it starts on 0. If it doesn't start on 0, you want from 0, how do you get there? Does that make sense, guys? You guys can give me a yes or no. Right? So this angle's on the inside. We got negative 53, right? But we want from 0 going around like that. So you're going to encounter that in your homework. Okay. Again, if they're in the first quadrant, it's really easy. If it's not in the first quadrant, you just have to do a little bit extra thinking. And I believe in you guys. I know you can think. Okay. I don't have a ton of time left, and I wanted to do at least 2 word problems. Do you guys, let's do this airplane problem. Okay. So we're going to have an airplane problem. Okay. So what we're going to do is we're going to find the components of an airplane. Okay. Now the airplane, and I'm just going to draw a coordinate system here, like all good physicists should do. So I have an airplane, and it's descending. And I'm going to draw a little airplane here. Oof. Looks more like a rocket. Okay, it's a rocket plane. Okay. Here, I can even put a little window on there. Okay, little windows. All right, so I have an airplane, and it's descending at 20 degrees from the horizontal. Okay, pretty good airplane, right? Looks kind of like a, what are those personal airplanes? The wings aren't very good, right? They should be more at an angle. Come on, Kraft, use triangles. There we go. Just ignore that other thing. All right, there we go. Fly like a G6, right? Okay. So, and then it has a speed, so it's descending at a speed of 150 miles per hour. Okay, that's its magnitude. Okay, so what we're going to do is we're going to find the components of the plane's vector. Oh my gosh, my handwriting is so bad. My hands are so cold that my hands are cramping up. Find the components of the plane's vector. Okay. Now, why would we do this? This is all sorts of important. The main reason why this is super important is wind. So if I'm trying to land and I know how fast the wind is coming from what direction, and I know what my components are, I can then correct my plane's travel so that I'm approaching the one-way straight on. Because if not, then my plane's going to tilt and I'm going to come at an angle. And I don't know if you guys have ever been in a landing where it's super windy and one of your landing gears comes in higher or lower than the other one. The landing's really rough. You kind of go, and then like your body's shaking up and down, and it's very stressful and not happy. Okay, so we're going to find the components of this. So to do that, what we're going to do is we have a magnitude and we have a direction. So what we're going to do is we're going to break up this triangle into X and Y spots, because this is going to be cosine of 20, 150. And this is going to be 150 sine of 20. Okay, now to prove that to you, right, cosine of 20 degrees would equal the adjacent over the hypotenuse. Okay, and the sine of 20 degrees would equal the opposite over the hypotenuse. Okay, and so if I solve these, I get 150 sine of 20 degrees equals y, and here I get 150 cosine of 20 degrees equals x.
Okay, so
okay, I'm gonna stop because really I'm doing the problem for you. I want to show you guys. You guys, and those of you who are in physics, you guys already know this, right? This is a free body diagram if you're doing forces, right? And all we're doing is we're taking one force and we're breaking it up into the x and the y. Okay, so if you're in physics, you've already been doing these. Okay, so for everyone else, I just want to make sure. So this is velocity, right? 150 miles per hour. So our velocity vector, oops. So if we call that v, so v then would equal 150 cosine of 20 I plus 150 sine of 20 degrees j. And that is our component form. Okay.
Now, again, the component form, you can always check your work, should equal the square root, right, of this hot mess. I don't agree with what the book does, so I'm not going to do that. Right? So you can check this because that should be 150, right?
So I just, hopefully this makes sense. It's a new notation. It's bringing all the trig in, but we've already done all of this. And so are you guys doing okay with this? I just want to make sure do you guys get the notation? Do you get the trig? It's a lot. And the reason why we picked 2 days, because if I did all of this and all of yesterday in one day, it would have been way too much in 50 minutes. So I really hope this makes sense. All I'm doing is that instead now of writing in component form,
right, instead of writing this, oops.
Right, instead of writing this, now we can write this, and there is so much more information, right? You get the magnitude, right? The 150 is the magnitude, and then the trig is your direction. Oh, shoot. You know what I did, guys? Sorry, I did physics. I called this 0. This is 0 in math. Sorry, in physics, this would have been fine, but this isn't fine. Oh my gosh. We need this angle, don't we? Didn't we just do that? We need that angle. Okay, so if this is 20 degrees, isn't this 180 degrees? So I need
180 degrees plus 20. Why am I doing that in a calculator? I'm embarrassed. That's 200 degrees. So I'm just going to go ahead really quickly and stealthily and add another 0 here. We want 200 degrees. Because remember, in math, if we're using math, 0 starts over here. In physics, I can just say, hey, what if we made 0 start here? Because in physics, you can do whatever you want. But since we're doing this in math class, sorry, I put on my physics hat, we need to go 180 plus 20. So this is really, right, 200 degrees. Do you guys see that? So this is 200 degrees from 0.
200 degrees from 0. So you would need to write 150 cosine of 200 I and 150 sine of 200 J. Sorry about that. Had on my physics hat. In physics, that would have been totally fine. In math, it's not. Sorry about that. Okay, so 200. 200. Now, this is still true, right? This is 20. But for our directions and our component stuff, we need to do 200. Okay, so this is still technically true. So in physics that we care about, but if we're talking about the vector, we're defining we're defining from 0. Okay. Oh my gosh, first day back. I hope she has a good time.
All right. For our last thing we're going to do today, we're going to do a boat problem.
Because I love boats.
Okay. So let's do it. So, boat problem. Okay. You're in a boat.
The boat has a vector b across a river with current c.
Okay. So you're in a boat. The boat has a vector b across a river with a current c. Okay. So c is the current of the river and b is going across. Okay. So c is,
let's do this in miles per hour. So how fast? Let's say that the river's going really fast. How fast? I'm not a river expert because I don't live next to one, but you guys in Mount Vernon do. Tell me, what's the miles per hour of a fast moving river? Is it moving like 10 miles per hour? Okay. But let's do let's go with that. Let's do I want to make it spicy though. Let's not make it boring. Let's say it's 10 cosine of 5 degrees and 10 sine of 5 degrees. Okay.
And then let's say the boat
is a vector, and I'm making this up, you guys can tell.
Let's just say it's going,
how fast do boats go? I was in a boat when I was a little kid, but I haven't been in a boat so long. 35, okay.
Okay, so let's say the boat is going 0 I plus 35 J.
Now, okay. Yeah, I think I'm okay with this.
Okay, I'm okay with this. So, can you guys find the resultant direction? That is, I have a river, I have a boat, right? I have a heading on the boat. I'm going that way. So I'm going to label this as JI.
You guys see my axes?
Okay. And so my boat's going this way. And my current is kind of going this way. Oops, C. Not G. C is for cookie.
Okay, I want to know what's your resultant vector. So what vector r will the boat be traveling on?
Okay.
Oof. I just made up this problem. Don't be mad at me. I have a thing for boats. All right. So let's see if you guys can do that. Ooh, I also wanted to do problem 80 with you. Am I going to have time to do this? So let's see. Yeah, I want to do this with you.
Okay, so let's just tidy this up a little bit. So if I add, so what I can do is I can just add C right here. Right? And then this is going to be R, right? So you can imagine the boat's trying to go straight across. C is going at an angle like this at 5 degrees. So R is going to be connecting those tips. Remember we talked about tip to tip last time? So then R here is going to equal, so I'd have to add these together, right? So it would be just 10 cosine of 5 degrees I, because I'm adding 0. And then here you would have to go plus, and then I'm going to put parentheses, 10 sine of 5 degrees plus 35 J. Okay.
So again, I did this as an example of how do you add vectors when it's in this trig form. So you'd have to use a calculator. You would have to go this plus this. So you'd have to go 10 sine of 5 degrees plus 35. Okay. And then that would be that. It's really easy. All right. Do you guys have any questions? I feel like maybe I'm treating you guys like, is this too easy? Am I going too slow? I don't know. It's really hard to teach this when you guys aren't here because I have no idea if you get this or not. Do you get what I'm talking about? Like if I have two vectors, you just add them? Okay. The last thing I want to do today then
is I want to do a word problem from your book. Oops, it has answers. Okay. So let me zoom in. We're going to do a physics problem. And you're going to have a problem just like this in your homework. Okay.
All right, so resulting forces. So we have forces with magnitudes of 2,000 newtons and 900 newtons act on a machine part at angles of 30 and negative 45 degrees respectively, which means that they're going in opposite directions, but darn do they respect each other with the positive x-axis. Okay. Find the direction and magnitude of the resultant of these forces. Okay.
So let's just do a little word problem together. So if you guys wanted a picture and you're like, crap, it says there's a picture. I forgot there was a picture. There we go.
Okay. So all it's asking you to do is, this is a basic physics problem. You have, so in this case, it could be two pieces of string pulling on the same, it looks like a metal latch. And it's just two pieces of string pulling on. So this might be at a dock. Okay, and you have two different strings tied to one loop on a dock, and you want to know what the resulting force is on that piece so you know how strong to make it. Okay, really cool example of physics. So to do this, basically there's two approaches you can do this. You can write each force in component forms and add them together, or you can do the physics way and find all the x components, then add them together, or you can find all the y components and add them together. It's both the same thing. So if you're used to doing it a certain way in physics, then by all means go ahead and do it, okay? So I hope you guys have had a second to look at this. I'm going to unfreeze and do this problem now. Okay. So we have, oops, I don't want you guys to see too much of my beautiful fake wood. You guys will get jealous. All right, so we have two components. So we have this component going up at 2,000 newtons, and it's at 30 degrees. And then I have this force going down at negative 45 degrees at 900 newtons.
Okay, so if I were going to write these as components, so let's say I call this A and I call this B. A would be 2000 cosine of 30 degrees, right? That's my x component. And then my y component would be 2000 sine of 30 degrees. And that's my y component. And it's that easy because you guys get trig. It's just a triangle, right? You guys see how this is just a triangle, right? So I'm just writing out the components, right? This is my magnitude. This is my direction. So I have this much force in my x direction, and I have this much force in my y direction. Okay, then that means that my b here would be, now I can't use negative 45, can I? Oh no, it says, yes. So it wants with respect to the x-axis, so not from 0. So you got to be really careful with that. In the word problem, it says with the positive x-axis. So it's not from 0. Okay, so everything can be a little bit different there. So we're okay to use negative 45 here. So this would be 900 times cosine of negative 45, I plus 900 sine of negative 45, j. Okay, so what you would do here is you would add these two, and you would add these two. Okay, now I'm not going to do this in a calculator, and but what you could do, the resultant, well, I'll do this. The resultant vector is going to be 2000 cosine of 30 degrees plus 900 cosine of negative 45 degrees, I, and then plus 2000 sine of 30 plus 900 sine of negative 45 degrees. And I'd get my calculator, get it out, and yell and shout. So let's go here. 2000 cosine of 30 plus 900 cosine of negative 45 equals.
Oh, shoot. That's why.
That's okay. All right. So, so what do we get here? 2068.45 I, and then plus, let's get the second one. 2000 sine of 30 plus 900 sine of negative 45. I should go to the fourth decimal. Okay. You guys see what I did here? I just plugged these in.
So it says it said find the direction and magnitude. Okay.
So this is still just component form, right? So the problem here is because I didn't keep it in terms of that, I have to find my magnitude in this. So to graph this, right, I'm going to have a point here, and it's going to be 2,368.447, 363.604, right? There's my point. And then it's above my x. So I'm going to have to find my theta. You guys with me on this? Am I going too fast? So I'm going to have to find my theta, and I'm going to have to find my magnitude. Okay. So to do that, to find theta, theta is going to be tangent inverse of sine, so 363.604 over 2,368.447, right? So I'm going to find that. So I type that into my calculator. What do we get? I get tangent inverse of 363.604. Now I know I'm rounding. I shouldn't be rounding. I'm running out of time. Okay. And I get, boom. So my angle is about 8.728 degrees. Okay. Which makes sense because if we look at this, right, there is more force going up, so we would think that it goes up a little bit, right? Okay. And then the magnitude is going to be my 2,368 point blah squared plus my 363 point blah squared, and then square root. So I'm going to do that in my calculator now. And blah is not an official term. So what are we going to have? 2,368.604. Oh, no, that wasn't the right one. 447 squared plus 363.604 squared, and my magnitude is 2,396 newtons. About. I rounded because I'm out of time. So I hope you guys, that was a really great example. This was problem 80 in the book. So if you guys want to write that down, this was problem 80. There's a homework problem just like it in tonight's homework. So what did I do? So first, I found the component form of each vector. I combined them to get a number. Then I can use right triangle trig to find the direction and the magnitude. Now, I'm